And our objective function is to minimize the number of cut edges, meaning the number of edges going from S to T, to the product of sizes of S and T. So the idea why we are interested in this problem, we want to find a small cut that cuts a small number of edges, but we don't want to get a trivial cut where we just cut one or two vertices.
Say it again, what is E of ST?
This is the number of edges
between parts. And this is the denominator, the maximal possible number.
Okay.
So it's just a fraction of used edges.
Yeah. And this problem often arises in divide and conquer problems where we have some graph and we want to divide it to sub-instances S and T, and we want to minimize the interaction between these two parts. And let's introduce a cut metric. So let's define a metric. The distance between two vertices of the graph x and y is equal to 1 if they belong to the same class. So either both of them belong to S or both of them belong to T, and to 0 otherwise. So here we relax the definition of the metric, and it can be the case that the distance between 2 points is between distant points is 0. Let's rewrite our objective function in terms of the distance function. So the number of cut edges is just the sum over all pairs U V, all edges UV, distance from U to V, right? If an edge, both endpoints of an edge are in S or in T, then this term doesn't contribute anything to the sum, otherwise it contributes 1. And this expression is just equal to sum over all pairs, not necessarily an X with an H, a distance from U to V, right? So this is our objective function, and like if you want to write an optimization problem, we say that dV is a cut metric. So far we didn't change anything, but now let's relax this condition. So let's actually replace this condition with the condition that dV is an arbitrary metric. Of course, if we change the condition, then the objective function can only decrease, because we are optimizing over a larger set, and this objective function potentially assumes smaller values, right? So if let's opt with the optimal value of the combinatorial problem. And LP be the value of the new program then LP is less than opt. Now, so if we consider this program, this is the objective function, and this is a constraint, that we can solve it in polynomial time. This is just a linear program. So for every pair vertices u and v, we introduce a variable equal to the distance between u and v. We write constraints that are just triangle inequalities and constraints that all the distances are non-negative. And this is our objective function. And we can efficiently solve it.
Again, I missed the point. So I understood the initial problem and also how you have defined the matrix. But
like if we consider this objective function with this condition, then this program is equivalent.
and what
to
are our
the
variables?
Metrics.
Variables is a matrix here of pairwise distances.
So, but the matrix is already defined on the left.
Of course. We want to find S and T.
Yeah.
But then instead of finding S and T, we find a D. But D depends on S and T, but S and T we don't know. There is a family of values. And then we extend this family, allowing any metric.
Not only 0, 1
Not only 0, 1 valued and
any.
And just then it becomes a linear programming problem, and then we have some optimal solution, and then we should do something to get S and T.
Why is it the objective function is not linear?
No, you want this be greater than C times this.
Some constant
Formally, we
C.
can write this. We want to maximize this, but
This is 1, for example, because we can multiply by any constant.
So you can write it like this.
Yeah. So now we have the solution for linear programming and want to do something.
And now we want to get back our cut. So what we do, we consider our graph equipped with the matrix B, which is the solution of our problem, and we embed using Bourgain's theorem into L1 with distortion log n.
Yeah.
So let's
Why L1? It's by Fréchet theorem.
But by Bourgain here.
Bourgain theorem.
In Fréchet it was L infinity.
Okay.
But now we have some distortion, which is log n. Yeah.
Yeah.
And
Now so for every x we have a random variable t, and let's assume as in the proof that it is bounded. Say that it lies it is between 0 and some constant m. Let's denote its action cx. So we now construct random paths. So let S consist of those vertices for which Cx is greater than or equal to, and now let's pick T, so we pick T uniformly at random between 0 and m.
What is m?
M is this constant. We assume that m is some upper bound on the value of all random variables. Okay. And let T be the set of those vertices for which Cx is less than T. So these are two random sets. And we have here two sources.
I mean, C is a variable, random variable.
Yeah.
How can you compare it with the real value?
So therefore S and T are random variables.
T is a random variable?
Capital S and capital T are random variables. Random sets.
I do not understand the inequality between Cx and T.
no, for some elementary events,
Huh?
for some elementary events, Cx is less than.
S of omega is a set such that Cx of omega is greater than
T of
Okay.
omega.
Okay, I see. Thank you.
T also depends on omega.
somehow. But it's another omega, not from Bourgain theorem. But
Okay.
special
Omega
view.
is from the Bourgain theorem, but S and T also depend on this random T,
Yeah.
so there are two sources of random assumption.
Yeah. And so what?
And this is our solution.
This is our solution.
But then
But
we
we
have to
need
check
facts,
to
not-
choose some specific value of
But we have a
This
randomized
hyperability is
algorithm.
good.
Sorry.
But
So we take a random omega.
we take a random.
And for with high probability we get something good.
Yeah. I'll prove that in expectation we get something good. I mean,
Okay, expected distance between S and T is close to this optimal thing, which is okay. So
yeah. So, for a fixed, what is the probability? Let's look at 2 points X and Y. What is the probability that the edge between them is separated? Probability that X belongs to S, Y belongs to T, X belongs to T, Y belongs to S. This is the probability that T lies between Cx and Cy, right? Or the other way around. And this probability is just equal to the expectation of the difference divided by m.
But we divide by m because we choose
Because
it not in
T should
zero.
belong to this segment, but so here we take the length of this segment and divide by the length of this segment.
I see.
And this is exactly L1 distance.
And this is exactly L1 distance between Cx and Cy, which is given by our solution.
is it your result? The
No.
last application. This.
No. This application is London.
Okay, this is just finished. This is exactly
Linear
L1
one.
distance, and we know which upper bound we know for it.
So now you know that this ratio for this distance function is equal to LP, just by the definition of LP, and it is at most opt. Okay, here so we are interested in this ratio, expectation of sum over all edges UV, distance between X and Y with respect to the scatter ST, and here expectation sum over all UV distance X and Y. So this is greater than that.
But so we obtain a solution which is at least log n times the optimal one. I mean,
So, yeah.
That's our goal at least.
So if we
We
had,
did it
if we didn't
already.
have any distortion, then we would just have L1 difference between X and Cy, and this would be equal to just the LP. But because we have distortion, we could lose log n factor. So we have this expression. This is equal to sum over edges UV Cx minus Cy. One more. And because our distortion is at most a log n, it is at most 12 log n times the same ratio for this LP solution. For the matrix that we get here, let's note this star. Here somewhere over all edges, and here over all pairs. And this is equal to LP, the value of the linear program, and this is at most, okay, get the square root program factor. So we get square root program approximation.
Yeah, so we prove that there exists at least one pair, at least one.
But we knew it in advance.
So actually, yeah, what we did, we definitely have the ratio of expectation, but we need like expectation of the ratio, but it's okay.
Sorry, would you repeat why you square in root distortion?
Oh, sorry. I'm sorry.
He didn't say it actually.
Oops.
I thought about the last result.
Oh well.
Sorry.
Yeah.
Sorry about that.
In this form is clear.
So you had designed an algorithm so that expectation of his performance is log n, so to say.
Yes. Yeah.
Okay. But also it can behave very badly if it is unlucky.
Yeah. But this can be, I think, randomized. At least this is not the most efficient way to think about it. Like you can, if you want to implement this algorithm, you need to do slightly different things.
Yeah, but you mean that for all this technique is you somehow really practically used in some real programs which do some real things to get real money or what?
I think this is advertised by people who work on this.
Yeah, so real money exists but no real programs, yeah.
I don't know.
Actually, they are not very real. Real gold.
Yeah.
Something real.
Yeah.
Okay.
Okay, so this is the end of the first part of
Let's thank Yury for the first talk.
yeah.
Maybe it's
Okay.
good to make 2 minutes break.
Yeah, so people who are afraid of semi-definite programming can say the limit out being final. But the coffee break will be next one.
Александр, вы нам не могли бы закинуть эту программу, проблему, задачу, о которой вы говорили? Если это вообще вежливо подать. Какой-то 16 на 16, там был квадрат, там что-то надо было вложить.
Если вы просто хотите файлы, то это раздел. Я думал, что вы хотите $1 миллион получить.
Было бы тоже неплохо, да. Нет, я бы посмотрел, но просто интересно. Да.
Нет, безусловно.
Нет, просто у тебя...
Я могу взять файл, но самого нет. Я могу взять
Ага, да, ну, например. Или послать, ну вот, если вы пошлете, например, вполне нормально будет. да.
Да нет, я могу взять с собой просто, это не проблема. Да. Ну и кроме того, я тоже про свидетелей, вы должны взять обещание, что если вы получите $1 миллион, то вы финансируете следующую конференцию CSR в России, правда?
На весь миллион? Не, естественно.
Нет, не на весь, ну зачем так?
Нет, если я получу...
Сколько потребуется, сколько этих документов, столько и дадим.
Можно так вместе в ближайших конференциях.
У вашего высокоуровневой беседы задаем технический вопрос. Технический вопрос первый. Бумажка не решилась?
Да нет, откуда?
Саш, вы что, не сделали?
Пошел писать.
Значит, второй вопрос. Мы здесь завтра встречаемся, происходит ли что-нибудь завтра?
Ну, я не знаю, если, в принципе, мои планы такие. Я для этого не обязательно, но мои планы такие. Я завтра с утра пойду в школу, и там, с одной стороны, там много часов 8, там все беседы, а еще у нас там 5-й и 6-й урок занятия. С 5-й и 6-й урок ну, до полчетверых. Ну, наверное, до 3, что-то, конечно, надо ехать.
То есть вы поедете прямо
Ну, школа-то в 15 минут, поэтому это 57-я школа.
Да, но не от вашего дома.
Да, но я поеду прямо из школы, да. Соответственно, в промежутке это я вполне могу зайти, если вы... Ну вот, я не знаю, есть ли в народе еще силы после этих самых...
Но мы все равно будем здесь, потому что исходство у нас попутно.
Да.
Вот. Во-первых, нас сюда пустят.
Ну, пустят, нет, все будет открыто. Нет, ну там на 3-м просто не закрывается.
А вы когда примерно сюда придете?
Ну это черт не знает, что там будет в школе. Там беседа зайдите, то, а если там будет какой-нибудь урок мира, там, труда и знаний.
Ну, я так просто выбираю Владимира.